Hi everybody, welcome to another video in differential equations, section 8.1. In this chapter, we will use power series to write the solution for differential equations. But first, let's go back and review some of the concepts in Calculus 2. First, the Taylor Polynomial approximation. So Taylor Polynomial, the formula for Taylor Polynomial of degree n, center at x0, approximating a function f of x is given by this. So the center is at x0, so we evaluate. So there will be a few components of the power Taylor Polynomial. So the first component is the function and derivative, second derivative, and so on. So this is the first component. We have the function, derivative, second derivative, and third derivative, and so on. So we have the n order of derivative. Evaluate at x0, which is wherever the center at. So we're going to have the derivative at that center point. Second, we're going to have the power series. So this is the power 0, the power 1. So we have this component. This we can say to the power 1. We have this to the power of 2, and then to the power of n. So that is the second component of a Taylor series or a Taylor polynomial. And the third one is the factorial. Originally it is divided by the 0 factorial. 0 factorial is equal to 1. So the first one is divided by 1. So that's why we don't have anything there. The next one is divided by 1 factorial. 1 factorial is also 1. And then we have 2 factorial, 3 factorial, and all the way to n factorial. With that, so the power series altogether, we have the n order derivative evaluate at the point x minus x0, which is the center, raised to some power, and divide by the factorial. The factorial would be the same as the order of the derivative. Right. So let's look at this example here. Determine the fourth degree Taylor polynomial for f of x equal to cosine of x at x0 equal to 2. Right. So first, the component of we have up to 4 degrees, so we're going to have the constant. First derivative, second derivative, and so on. So up to 4th. So we go up to 4th degree, or the 4th derivative. So the first one, of course, is this column. Also this column. So we have originally the function is cosine of x. So we start with cosine of x and take derivative. Negative sin x, negative cosine x, sin x, and cosine x. So we just take derivative here. That of course indicated by the derivative. And then next, we evaluate the derivative at x equal to x0, which is 2. So when x equal to 2, we're going to have this function at 2. Right, so that's first component. And then next, we divide by the factorial, the same order as derivative. So divide by 0 factorial is 1. 1 factorial also 1, and so on. So once again, we have the function derivative. Just keep taking derivative, and then put in the numbers, the center, substitute in for x, we have the functions, and then divide by the factorial, and then finally we have those coefficients multiplied by the power of x minus 1, x minus 2, sorry, that gives us the power series. So this one to the first power, this one to the 0 power, and we have the power series, this one up to the 4th power. And the coefficient here we have cosine 2, negative sine 2, negative 1/2 cosine of 2, and so on. So this coefficient will multiply by x minus x naught to the power of j. The reason we use j here because the index sometimes it is the complex number, and then we try to avoid I, so we use j instead. But once again, when we do this derivative, keep taking derivative and then put in the values, and after that evaluate, put in the values, and then divide by the factorial, and at the end we just multiply by it. Right. Now let's just go to this one. Write the first 3 non-zero terms for the Taylor polynomial that approximate the function sine of 2x. So the function is sine of 2x and center at x. So we're going to make a table. Right. Right. We don't know how many terms we need, but we need the first 3 non-zero terms. So it might be more than the first 3 terms. Yeah, the terms could be equal to 0, but what we want here is the first 3 non-zero terms. I should have the table there already. Right. Right. So we just go until we have the first non-zero coefficient. Right, so this might be more than enough. Right, j. Next we will take the derivative. X is the variable. Now we take derivative, but evaluate at x not which is 0, so we just evaluate at 0. X equal to 0, we have this, and finally we'll take that coefficient, divide by the j factorial. Right, let's go. Right, so the first, when j equal to 0, we have the function sine of 2x, and then we're going to put 0 in it. Sine of 2 times 0. That gives us sine of 0. Sine of 0 is 0. Well, that means we're going to need a few more terms because we want the first 3 non-zero terms. Right? So and then we divide by the j factorial. So 0 divided by the 0 factorial. Of course, that's still 0. So the first one is 0. Next, when j equal to 1, we're going to take derivative of this. Derivative of sine of 2x is cosine of 2x times derivative of 2x, which is 2. So this gives us 2 cosine of 2x. And then we have 2 cosine of 2 times 0. Cosine of 0 is 2. I'm sorry, cosine of 0 is 1 times 2 is 2. And then 2 divided by the j factorial, 1 factorial. 1 factorial is 1. So we have 2. Right, j equal to 2. Keep taking derivative of this, which gives us negative 4 sine 2x. Well, that's going to give us 0 again, because sine of 0 is 0 and this one is 0. And then we have 0 divided by 2 factorial. It's still 0 anyway. 2 factorial is 2. Right, so far we only have one non-zero term. Right, next 3. We take derivative of this. There will be an extra 2, negative 8, derivative of sine cosine, and then there's extra 2. Right, derivative of sine is cosine, and then we have derivative of 2x and give us 2. Right, then we're going to put 0 in for it. Cosine of 0 is 1. That gives us negative 8. Now we will have negative 8 divided by 3 factorial. Just a reminder, 3 factorial, n factorial is n times n minus 1. The product will go all the way back to 1. So 3 factorial is 3 times 2 times 1, which is 6. So I have negative 8 over 6, which reduces to negative 4 over 3. Right. Next, so far we have 2 non-zero terms. Next, derivative of this. Derivative of cosine is negative sine, so that turn to positive now. Sine of 2x, 16 sine of 2 times 0. Sine of 0 is 0, so this one is 0. 0 divided by 4 factorial. Doesn't matter what 4 factorial is, it's still 0. But 4 factorial is 4 times 3 times 2 times 1. So pretty much it's 4 times. Later on, if we want to go to 4 factorial, we can just say 4 times 3 factorial, right? So, because to evaluate the big factorial, we can just go to the smaller one. For example, if they ask what is 10 factorial is, we can say 10, 9, and if we want to stop, we can just stop there. And of course 8, meaning we go 8, 7, 6, 5, all the way back to 1. Right, so which means we just take this factorial, multiply by 4. So 6 times 4 is 24. That's 0. Now 5. Derivative of this is 32 cosine of 2x. 32 cosine of 2 times 0. Cosine of 0 is 1. And 1 times 32 is 32. Now we have 32 divided by 5 factorial. 5 factorial is 5 times 4 factorial, which is 24 times 5 will be 120. Right. So look like 2 over 15 perhaps. Sorry, 4 over 15. Right, so we have 3 non-zero terms, 1, 2, and 3. Okay, that's good. And then we write the Taylor polynomial. This one up to order 5. So we have p of 5, p sub 5 of x. Right, now we write first the non-zero term is 2. And then we will have multiplied by the power x minus the center 0, right? Now the 2 here when j equal to 1, so that to the first power. Right, next we have negative 4 over 3. And then x minus the center negative 4/3 when j equal to 3. And then plus 4/15 and then we have x minus the center x minus 0 4/15 corresponding to 5. So that's what we have. So this is the 5th degree polynomial, and that contains the first 3 non-zero terms. Right. Of course, we're not going to write like that. We just say this is going to be 2x minus 4/3 x cubed plus 4/15 x to the 5th. Right. So that is the 5th degree polynomial approximation for sine of 2x center at x equal to 0. Right. So simple now. Just a review of what we have in calculus 2. Right. Now we go to complete the different things. Of course, this is differential equation, so we have to use differential equation. So this is completely new. Right. How do we approximate solution for initial value problem? So let's find the first 5 terms of the Taylor series that approximate the solution of the initial value problem at x equal to 0, y second derivative equal to 3 derivative plus x squared y, and the initial condition is that. Right, so we're going to write the solution. First we write the first 5 terms, so it's going to be the first 5 terms will be up to the 4th power, right? 0, power 1, power 2, 3, and 4. So regardless of what the answer is, the Taylor polynomial take this form. Right, just go there. Right, now we have the function equal to 10, so that's easy. We can just substitute the values of the function equal to 10. Now the derivative equal to 5. So at least we have the first 2 terms. Now to get to the next terms, we just take the second derivative, third derivative, and fourth derivative, and so on. If we have the derivative at 0, then we're done, right? Okay, so how do we do that? Right, okay, first of course we have the y of 0 equal to 10, derivative at 0 equal to 5, so we can substitute here 10 and 5, which is good. Now we just need to find all the derivative. Right, so here we have the second derivative is 3 times the first derivative plus x squared times y. Why don't we start with that? All right, we'll rewrite that. Now, we just rewrite the function, the equation here. Now, when we do this, evaluate at x equal to 0. At x equal to 0, we have the second derivative at 0. The derivative evaluate at 0. We have x equal to 0. The function evaluate at 0. So we just put 0 in for x. And so we have 3 times derivative times 0 square times y of 0. So that's what we have. 0 square, 0 times 10 is 0. 3 times 5, 15. So the 15 will go here. Now, if that is the case, if we take derivative from here, we will take derivative. I will write from here to there, we differentiate. So differentiate, take derivative, second derivative, take derivative, of course that's the third derivative. Derivative, take derivative again, that's second derivative. Now, pay attention to this. We have x squared y, right? Both of them have x. X squared has x in it, y we have x in it. So this is a product. That product requires the product rule. So x squared to x times y and x squared times y prime, right? And now it's easy. We just take derivative. Put 0 into it. Right, it will be easy if we have 0. So put 0 here, and then 0 here, and the function evaluates 0. X equal to 0, the function evaluates 0. So we have all of that. Good thing when we have 0, that go to 0, that go to 0, and 3 times the second derivative. Second derivative is 15. We already have that earlier. So we're going to substitute into the second derivative at 0. That is 3 times 15 is 45, and that's what we have. And then, so we will keep differentiate. Keep differentiate. Second derivative again is 3 times the derivative. Now, notice that now we have two terms. The 2x, y is a product rule. Will give us this 2. And x squared prime, y prime, using the product rule, will give us these 2 terms. Right? Derivative of 2x is 2, and then y. Derivative of x squared, 2x, and then y prime. Right? And then derivative of that 2x and derivative of y. And then derivative of x squared, 2x, and then y prime, and then x squared, derivative of y. And then we just put 0 in for x and the function and the derivative. We do that. This we have 0, so that's 0. This has 0 as well. This has 0 as well. So we're left with 3 times the triple derivative, 3 times 45, plus 2 times the function, and that 155. And finally, we substitute into this, right? So we have the values 10, 5, 15, 45, 155. Those are the values. So we're going to substitute in 10, 5, 15, 45, and 155. Those are the values of the function, derivative, first derivative, second derivative, third derivative, and fourth derivative at 0. And then we divide by the factorial, of course. And then we should have x minus 0. Just like the last problem, we can write x minus 0 to the first power. But of course, that's just x. So that's why this becomes x squared, x cubed, and x to the 4. Because this one is centered at 0. So we have x minus 0 raised to the power. Right. So that's what we have, right? So simple enough. First, we write the power, the Taylor, the power series, or the power polynomial, and then we're just going to put the values in the evaluate. Try to find everything we know. Just keep on from there. Right. Next, I'll find the first 4 terms of the Taylor series that approximate the solution, derivative of y equal to x squared plus y squared. Right. So regardless of whatever the problem is, the Taylor series or Taylor polynomial, that's the first thing we'll start with. So first, Taylor series, first 4 terms of Taylor series. First 4 terms of the Taylor series or the Taylor polynomial. Alright, so let's write out. So the first 4 terms, so we start with 0 power 1, 2, 3. So we only stop at 3 power. So P3 of x. We have the function, which is 1. The derivative times x. because this one is 0 Taylor series. And by the way, in calculus 2, when we say the Taylor series at x equal to 0, that also have the name is Maclaurin series. So that center is 0 because we have y naught equal to 1. So that's why we have the center at 0. So we have that. And then we have the second derivative divided by 2 factorial. This one divided by 0 factorial, divided by 1 factorial. We don't need to write it. And then this we have x squared. And then third derivative over 3 factorial x cubed. Right. So we want the first 4 terms. That's the first 4 terms up to cubit of x cube of x. First, no power, first power, second power, third power. Right. So that's the first step. Next, what do we need? We have y not equal to 1. So let's start with that. Y at 0, not y not, sorry. Y at 0 is equal to 1. Okay, that's what given. Right, so we have 1. Next, we have the derivative equal to x squared plus y squared. Now, if we evaluate at x equal to 0, so put 0 in the derivative, 0 for x, and y of 0. By the way, y squared, so we evaluate y of 0 first, and then we squared. Right. 0 squared, 0. Y at 0 is 1. So 1 squared is 1. So the derivative is equal to 1. So because we can say this is derivative at 0. Now, to get to second derivative, of course, we're going to take the derivative of this. So of course, we just differentiate. We have second derivative easily. Derivative of x squared to x, derivative of y squared. Notice that since y is a function of x, so not only we have 2y, we have to have y prime as well, because y is a function of x. So this is implicit differentiation. If it is x, then we don't have anything, because that's just x. Now y has x in it, so we have to write like this, which is the chain rule. Now we evaluate at x equal to 0. Right, so we have y second derivative 0. We have 2, x is equal to 0, plus 2y of 0, y naught of 0. Right, 2 times 0 is 0, 2 times y of 0 is equal to 1. Derivative at 0 is also 1. So that gives us 2. So that's the next coefficient. We'll check derivative again. That gives us the third derivative. Derivative of 2x is 2. Now, derivative of this, that is a product rule, so we have to be a little more careful there. So first derivative of 2y is going to be 2y prime, and then we have y prime, right? And then plus 2y and then y prime, y double prime. Right. Now, evaluate at x equal to 0. Now, y cubed of 0 will be 2, right? Plus 2 times y prime. What is y prime? It's 1. Oh, let's just put the so yeah, I'm going to put in the 0 first, and then so the derivative is 0, right? That's better. 2 times the function at 0, second derivative at 0. Right, so we have 2 plus 2 times derivative at 0 is 1. Derivative at 0, 1, plus 2 times the function is 1. Second derivative is 2. So I mean we have 2 plus 2, 4, plus 4 is 8. Right. And that equal to the third derivative. At 0. Right. And finally put it back into this form. We will have P sub 3 of x. So the third degree Taylor series y at 0, which is 1. Plus derivative at 0, which is 1, times x, plus second derivative, which is 2, divided by the 2 factorial x squared, plus the third derivative, which is 8, divided by 3 factorial x cubed. Right, so we have 1 plus x, 2 factorial is 2, 2 over 2 is 1, so plus x squared, and then 8, 3 factorial is 6, so we have 1 plus x squared, 8 over 6 cancel out, we have 4 over 3 x cubed. Right, so that's what we have. Right. So pretty much it just use the Taylor series, and we try to figure out what is the function derivative and second derivative and so on. Right, now next find the first 6 non-zero terms for Taylor series. Well, actually, just make things easier. Just ignore the non-zero terms. So when we know there are 6 terms in the Taylor series, we know what power do we need to stop at. Right. So of course, first, we're going to write the first 6 terms of the Taylor series. Once again, this is centered at 0. So first 6 terms. If we don't know how many terms we need, like the 6 non-zero term, we have to write a series very long, and then we determine later. But let's this one to say 6 terms. The Taylor series center at 0. Because we have 0 here. Right, center at 0. Right, 6 terms, so we go from 0 degree, so we will be stopped at the 5th degree of x. Right, so the function has no degree. First derivative, first power of x. Second derivative at 0 have to divide by the 2 factorial now. X squared. Third derivative 3 factorial x cubed. Fourth derivative evaluate 0, divide by 4 factorial x to 5th, and then the 5th factorial, this to the 4th. Divide by 5 factorial x to the 5th. Right, yeah, 1, 2, 3, 4, 5, 6 terms. So from 0 degree to 5th degree. Right, so that's what we have. Now we're just going to find all the coefficients. We are given a0 and a1 for the function and derivative, which is good. So y0 is equal to a0 and the derivative at 0 is equal to a1. And then the second derivative and so on. So starting from the second derivative, we have y second derivative plus x squared times y equal to 0. So move the x squared y to the other side. So we have y second derivative is equal to negative x squared times y. That's easy enough. And then evaluate at x equal to 0. We have y second derivative at 0. Put 0 for x. And 0 is a variable of the function y. There's 0 there. 0 times anything is 0. Right, so that's good there. Next, we have the second derivative. Now we go to the third derivative, fourth and fifth. We can have this is the second derivative. We're going to differentiate second derivative, take derivative one more time to give us the third derivative. This require a product rule. Derivative of negative x squared negative 2x times y and then we have negative x squared times y prime. Right, so that's just a product rule. Is equal to 0, so y cubed, the third derivative of y at 0, put 0 in for x, y 0 minus 0 square y prime of 0 right. We have 0 here times anything is 0, 0 times anything is 0, so the third derivative is equal to 0. Then you say, what happened? Could it be all of them equal to 0? And of course that could be, but this one we want to write the first 6 term of the Taylor series, so we're going to write to the fifth power or the fifth derivative anyway, so we keep going with that. So we have this and check derivative. Both sides. Derivative of the third derivative, by the way, let's just write this is the second derivative at 0, the third derivative at 0. So the fourth derivative. Once again, this is the product rule. Give us negative 2 times y minus 2x times y prime. And then this is also a product rule, negative 2x y prime and then negative x squared y double prime. We're going to evaluate at x equal to 0. Of course later on we know that every time that have x in it, it's going to be 0, so all of that is 0. But let's just do that slowly. Right, put 0 in for x and the variable for the function y derivative and then second derivative. So negative 2 y of 0, negative 2 times 0 y prime of 0 minus 2 of 0 y prime of 0 minus 0 square y double prime of 0. Right, so what do we have here? Right, that has 0, so go to 0. That one has 0, go to 0. That go to 0. Y of 0 is equal to a naught, so negative 2 a naught. We take derivative again because we're going to go to the fifth order, the fifth power, the fifth order derivative and over 5 factorial, right? So derivative of this, right, so this is the fourth derivative. We assume that it's not going to be 0, otherwise all of that's going to be 0. Right, so the fifth order derivative. Now, the first one is not the product rule, so just negative 2y give us negative 2y prime, right? And then next all of them is going to be a product rule. So that first term, product rule, negative 2 y prime, negative 2x y double prime, product rule, right? Derivative the first with the second, the first with the derivative of the second, minus 2 y prime we're doing this one now, and then minus 2x y double prime right, and this minus 2x y double prime minus x squared y triple prime. Right, so except for the first one, everything after that is the product rule. Now we're going to put 0 in for x. And then minus 2 y prime of 0 minus 2 0 y double prime of 0. Okay, 1 2 3 4 1 2 3. Okay, this one minus 2 y prime of 0. Actually we should combine just 1 2 and 3 of them, yeah, but anyway, 2 of 0 y double prime of 0 minus 2 of 0 y double prime of 0, and those two can combine as well, minus 0 square y triple prime of 0. Right, so this one has 0, so that goes to 0, this go to 0, this go to 0, this one has x, which is 0, go to 0. So how many we have? Negative 2, negative 4, and negative 6. And what is y derivative of y at 0? Would be a1, right? So the function derivative, second derivative, third derivative, fourth derivative, fifth derivative. I put all of them back into the power series. Right. The function a naught plus, so let's write that in. Derivative a1 x plus second derivative, that is 0. Yeah. Third derivative also 0. So that's why we don't want the first 6 non-zero terms, which means we have to do 2 more. And potentially they can still be 0. So that's why we stop only at 6 terms. With 3 factorial x cubed. Fourth derivative is going to be that over 4 factorial x to the 4th and then negative 6 a1 over 5 factorial x to the 5th. Right, now just simplify a little. A naught plus a1x, that's 0, that's 0, minus 2 over 4 factorial minus 2 over 2 a naught over 4 factorial is 4 times 3 times 2, 24, x to the 4th minus 6 a1 5 factorial will be 5 times 4 times 3 times 2 times 1 will be 1 over 120 x to the 5th. And finally we can write a naught plus a1x 2 and 24, that's 1 over 12 a naught x to the 4th, and 6 and 120, that minus 1 over 20 x to the 5th. Right. Of course, if we have to go further, we're going to take the derivative of this and just keep going further. In that case, we might want to simplify this first and recognize that every time we have an x, that's going to be 0. So that makes sense. If we have to go further, then we have to recognize some pattern. Otherwise, if we just keep taking derivative, it's going to be a little bit of work. Right? So, yeah. So in this section, we just need to know the Taylor series. If it is standard 0, we call that Maclaurin series. Maclaurin series, which is Taylor series, center at 0. Right. So we need to know the Taylor series, of course, Maclaurin series, and then how to use that. So we just have the function derivative, first derivative over the factorial raised to the same order. I mean, factorial of the same order, like 2 factorial under the second derivative, 3 factorial under the third derivative, and then so on. And then we have x minus the center raised to the power of n. So all of that, the power of the factor, the order of derivative, and the number raised to the number factorial, all of them have to be the same number. Right, and of course with that we can write solution, series solution to a differential equation. Of course, if this way we can write more term if we need to, but for practical purpose, usually we stop at some number of terms. We can, if we have to write more terms, we should recognize the pattern and write that as a summation. Right, and this section with the little theorem, it says that the arrow bound for the Taylor polynomial is given by that, where this is the Greek letter Sine, and so we have if we stop at the n polynomial, then the next term evaluate at some point between x and x naught is going to be the error of the polynomial, Taylor polynomial. Right. On this section, we focus more on that because the theory here, the theorem here is a little bit advanced, so we will not go over that. But need to know how to do the Taylor series and use the power series to write the solution to a differential equation. Right. So that's all we need for this section. As always, thank you for watching and see you in another video in differential equations.